Stick your head out the window of a car going 60 miles an hour. It is loud, chaotic, and impossible to catch your breath. Now imagine trying to take a smooth, steady breath while flying at 600 miles an hour through the freezing sky. An airplane engine needs massive amounts of air to run, but if that air hits the internal blades as a chaotic hurricane, the engine chokes. So how do we get perfectly calm, smooth air into an engine tearing through the sky at top speed? Welcome, future pilots. Today we are looking at the very front of the engine, the air entrance, or inlet. Think of it as the airplane's nose. Instead of an open gap that passively swallows whatever comes its way, it prepares the air before it ever reaches the spinning blades inside. If you are starting your aviation journey and want to understand how airplanes actually work from the ground up, make sure to like this video and subscribe. We are here to help you build that foundation. The inlet is a hard-working respiratory system. By the time the air passes through this first stage, it is organized and conditioned, giving the engine exactly what it needs to produce power without wasting any energy. Think about an athlete running a marathon. To keep their muscles working, they need steady, rhythmic breaths, not frantic gasping. The engine operates the same way. It needs the air to move in straight, organized lines to perform efficiently. The specific, slightly curved shape of the inlet tunnel acts like a comb for the wind. As the turbulent sky enters the duct, the shape physically straightens out those chaotic swirls, sliding the air down the tunnel without it catching on the sides. As the air moves through this shaped tunnel, it also gets squeezed. This creates a natural buildup of pressure before the engine's internal fan blades even touch it. This boost, the compressor pressure ratio, means the air leaving the duct is significantly more packed and powerful than the air that entered. By taking messy, fast air and delivering a smooth, high-pressure stream, the inlet gives the engine free power, making the aircraft perform reliably. Because airplanes do different jobs, they wear different kinds of noses. Large passenger jets use enormous turbofan engines. Their inlets are massive, wide-open tunnels bolted to the front, designed to swallow tremendous volumes of air. With a huge fan spinning right at the front edge, these engines can be incredibly loud. To fix that, the walls inside these massive inlets are lined with sound-absorbing materials. They soak up the roar of the spinning blades to keep the flight quiet. Planes driven by propellers, known as turboprops, deal with a different environment. They often fly closer to the ground or land on dirt runways, facing a higher risk of sucking up rocks, dust, or low-altitude ice. Because of those hazards, turboprop inlets are heavily guarded. They use built-in screens and curved metal vanes, acting like a thick scarf pulled over a mouth, to physically block heavy debris or bouncing ice chunks away from the delicate engine parts. Where the plane flies dictates how it breathes. High-altitude jets get giant open intakes, while low-flying workhorses get tightly guarded filters. High in the clouds, freezing temperatures are a constant threat. If ice builds up on the front rim of the inlet, heavy chunks can snap off and get sucked into the spinning fan blades at hundreds of miles an hour, which would destroy the engine. To fight this, the engine acts as its own heater. Deeper inside the engine core, the air gets incredibly hot. A system of pipes extracts some of that scorching air and routes it right back up to the front rim. This hot air flows through the hollow metal ring around the intake opening. It turns the very front edge of the engine into a hot surface that melts moisture on contact before it has a chance to stick. The engine sacrifices a tiny bit of its own heat energy to build a thermal shield, neutralizing one of the biggest atmospheric threats in aviation. Now, let's look at military aircraft designed to fly faster than the speed of sound. Even if the plane is flying at these extreme speeds, the air hitting the internal engine blades must stay below the speed of sound. If it moves too fast, the resulting shock waves would tear the engine apart. Think of catching a 100-mile-an-hour fastball. You have to pull your glove back smoothly to absorb the energy. To catch a supersonic wind, these intakes use a tunnel that narrows down and then opens up again. This geometry creates a physical barrier that forces the air to drop its speed before it reaches the fan. For these high-performance jets, the air entrance is a traffic calming zone. It takes violent winds and tempers them into a manageable, highly pressurized breeze. This intake is doing a dozen jobs at once. It is a traffic controller for the wind, a heater for the ice, a muffler for the noise, and a pump that builds pressure before the engine even turns over. For anyone learning to fly, the lesson here is that an engine is only as healthy as the air feeding it. Delivering a clean, steady stream of wind guarantees a reliable flight and keeps everyone safe. The next time you walk onto the tarmac and look at the front of a jet, you will see a system that physically conditions the atmosphere so the aircraft can breathe. Grasping how these foundational systems work beneath the surface is exactly how you transform from a curious aviation student into a confident, knowledgeable pilot. Keep studying, and we'll see you in the skies.